In the previous chapter, we explained that all of physics can be summarized in how nature is vague and tries to optimize action in all processes, and that physical law was general. But there is another set of famous laws that also have a very extensive range of application. Let's talk about the laws of thermodynamics. When doing physics, we analyze systems made up of components that interact with each other. But for reasons of pragmatism, we cannot analyze absolutely everything in the universe and its interactions if we want to be able to progress. Therefore, we have to make simplifications or approximations and focus on the most important aspects, on what most affects the evolution of the system we want to analyze. There is a classic example of this, the free fall of an object. If we want us to analyze everything in detail, we must consider that Earth's gravity changes with height, also that the effect of the Sun and other planets is present, as well as the effect of air, pressure, and temperature, the internal interactions between atoms and those of the object. Even light, when it hits an object, also pushes it a little. Do we normally take all this into account when we see an object fall? Obviously not. Why? Because to know things like how long it will take for the object to fall or at what speed it will reach the bottom, it is not necessary. You simply have to sacrifice precision. That is to say, we might not be able to know with 5 decimal places how many seconds the fall lasts, but we can with 2, for example. And therefore, whenever we analyze a problem, we can distinguish 4 systems. The first of them is the study system, which is everything we analyze. The second is the internal system, the internal components of our study system, that is, the particles that compose it and their interactions. Then we have the third, the external system, the external components that we are not analyzing. And the fourth, the union of all the previous ones, the universe system. In our example, the study system would be the falling object and gravity. The internal system would be the particles that form the falling object with their interactions. The external system would be the air, the sun, and the other elements surrounding the system. And the university system would be the whole set of all of it. We usually do not analyze the internal system in detail because it is practically impossible. Let's say the object that falls is a tiny iron ball of 10 grams. In just 1 gram of iron, for example, there are more than 10 to the power of 25 particles, counting the quarks. If we had to analyze each one of them to evaluate how a ball falls, we would never finish, and therefore we give up analyzing that internal system. In the same way, we do not consider the effect of the sun's gravity or the moon's, which would also be external systems. In thermodynamics, we could say that it is the branch of physics that tells us how to handle these internal and external systems that we do not analyze in detail, but that are there. A branch that introduces us to 2 crucial concepts for analyzing the world we live in. The first of these is temperature, which is usually introduced as a way to measure how fast the particles of the internal system move. The higher the temperature, the greater the speed of the atoms. And this, for example, is the heart of the kinetic molecular theory. In a solid at low temperature, the particles are more or less still, forming stable structures. In a liquid with somewhat higher temperature, the particles have greater movement and the structure deforms, although it still maintains a certain cohesion. Lastly, in gases, the particles move so fast that they are more or less free and no aggregation structure can be observed. And zero temperature, better known as absolute zero, would be a state of absolute stillness. This definition of temperature is problematic since higher temperature does not always indicate a greater degree of movement, and if we believe it, we will be surprised to discover that there are physical situations where one can talk about negative temperature below absolute zero. Why? Because temperature is more complicated. And to understand this, we have to talk about the wonderful entropy. It is common for entropy to be presented to us as a measure of the disorder in a system, but that is not very rigorous either. It would be like saying that summer is the time of year when it is hot, Normally it's true, but it's not the correct definition. And the analogy is very fitting, because when we talk about entropy, we're actually not talking about physics, but about combinatorics, simple mathematics, and in particular, simple logic. Let's say we have a system of two coins that can show heads or tails. And let's suppose we have no idea about the exact situation of each coin. There are four possible states. Both are heads, both are tails. The first is heads and the second is tails, or the first is tails and the second is heads. Well, entropy is nothing more and nothing less than a way to measure how many possible states there are in the system on a logarithmic scale. With two coins, there are 4 states, and with 3, there are 8, and with n coins, there are 2 raised to the power of n states. And given that the number of states can grow exponentially with the number of elements in the system, and in a standard system there are more than 10 to the power of 23 particles, the logarithmic scale will help us handle smaller numbers. And furthermore, using logarithms means that if there is only one possible state, and therefore we know the system exactly, the entropy is 0. And this order also means that the system allows, the less we know about it, and the more ways it can manifest, the greater its entropy will be. That is why entropy is often associated with disorder. But let's return to our coin system. If we had to bet that both are heads, both are tails, or each is different, what would we bet on? Because each would be a different thing, for the simple reason that there are twice as many chances to be right. And that is the situation of greatest entropy and disorder. If both are heads, we know the whole system. And if both are tails, also. If each one is of a different type, we don't know which is heads and which is tails. And therefore, if we have to bet on the situation of greatest ignorance or entropy. And furthermore, if we have, for example, a system of 1000 coins, by simple probability, we can conclude that if each one can switch from heads to tails, or vice versa at any moment, it is most likely to tend towards 500 heads and 500 tails, the situation with the greatest possibilities and entropy. Therefore, when physicists talk about the second law of thermodynamics, that entropy tends to increase over time, it usually does. The only thing we are saying is that what is most likely to happen is literally the most probable. It is a tautology, an obvious statement, seriously. And it turns out that the temperature of a system measures how much the energy changes with entropy. As normally greater entropy implies greater energy, the temperature is usually positive. But in certain circumstances, to increase entropy, the energy must be reduced, leading to negative temperatures. But let's reason out another spectacular thing. Let's say we have two systems, for example, an oven and a pizza, and each of them has its own energy and entropy. If the oven has a higher temperature, that means it requires more energy to increase its entropy. And therefore, if the oven and the pizza come into contact and seek the greatest possible entropy, that is the way to arrange their particles that leads to the greatest possible disorder, the oven will transfer energy to the pizza. Why? Because the oven will lose entropy, but the pizza will gain much more due to its lower temperature. And when will the energy transfer from the oven to the pizza stop? When their temperatures equalize, when it costs both the same energy to increase their entropy. For this simple reason, all systems, when they come into contact and can exchange energy or even particles, end up equalizing their temperatures while keeping the total energy of the system constant at all times. The total energy is conserved, the temperature equalizes. The entropy is maximized. Do you remember the previous episode? Let's talk about optimizations again. We do not know what each exact particle of the system will do, but overall it will seek to maximize entropy while keeping energy constant, and as a result, the temperature will try to be the same everywhere. So, to recap, in physics we have to make approximations because it is impossible to analyze everything in detail. When we are unaware of things in a system, always, except for isolated particles, we can assign it entropy, and it is expected that entropy tends to increase. Entropy will increase while respecting the conservation of energy, so whenever two systems interact, the energy one loses is transferred the amount que the one transferred to the other. And with this, we see that physics also draws heavily from concepts of combinatorics, statistics, and probability, which are crucial for this type of analysis. And I also want to emphasize that while in the previous class we talked about physics, in this one we have really only talked about logical concepts that must work no matter what, because physics is logical. And thermodynamics, which is the branch of physics that combines the concepts of energy and temperature through entropy, therefore, probably at the end of the year, will also work in all areas of physics. For this reason, it is often said that if a theory is incompatible with the laws of thermodynamics, it has a problem, which, on the other hand, has been an important beacon for evaluating theoretical proposals in the history of physics. For example, when radioactivity was discovered, it seemed that certain types of decay did not conserve energy. And what happened? To conserve energy, it was proposed that there were unknown particles carrying away the missing energy. And that's how the neutrino was discovered. A similar story can be told about the discovery of gravitational waves when observing how a stellar system seemed to lose energy. And all this leads us, of course, to the conclusion that we should never trust anyone who claims to have energy from nothing or to achieve systems where entropy does not tend to increase, because no matter how much a process can be complicated, in the end it will adhere to the laws of logic and minimal action. Lastly, the range of application of all this is enormous, from the analysis of the molecular behavior of solids to quantum gravity theories, which are currently trying to make black holes compatible with thermodynamics, to the analysis of the viability of nuclear processes in stars and whether they will be spontaneous or not. Thermodynamics, in short, is everywhere in physics.